Questions from lesson 2? What number?
What was the direction for question 2?
For question 2? Sure thing. Okay, so the direction, current is moving this way, and the magnetic field floating in midair. Okay, so the fact that it's floating in midair, gravity's pulling it down, that must mean the magnetic force is this way. All right? So if I point my right thumb in the direction of the current, now when we did our right-hand rule, which way told us the force? Which way what pointed? A palm. So I know the force has to be up. I know the current is going to the right. Which way are my fingers extending? You know what? That has to be a magnetic field into the page. So with this right-hand rule, now, Megan, it's fair game for me to give you any two of the directions and find the third one. I can either say, here's the current, here's the magnetic field, which way is the force? Or, hey, you know which way the force is, you know which way the magnetic field is, which way you have to send a current through the wire? That way or that way. Or you know the current, you know the force, which way does the magnetic field have to be? Okay?
So you put your thumb in the direction of the current.
Okay, first of all, you're holding your paper wrong. Get it out of your binder and hold it facing you. Okay? Hold it vertically like here.
Okay.
And we're going to be flogging the right-hand rule some more today and next class. So that's why I said if you're still lost by about by about Wednesday of this week, then freak out. Ready? Right thumb in the direction of the current. Now, normally you'd point your fingers like you're giving a high five in the direction of the magnetic field. They didn't tell you the magnetic field, but they did tell you the force. It has to be up. Even if they hadn't told me that, the fact that it's not falling, I could have said, well, gravity down, there must be a force up because of the free body diagram. So palm told you the direction of the force, which means I go like that. Your fingers tell you the direction of the magnetic field. The magnetic field must be into the page. Must be into the page. Oh, and then the magnitude is FB equals FB. Bill equals MG. What do they want you to find? Magnitude of the magnetic field. Oh, and they went micro Teslas for some reason, so it's going to be 10 to the negative 6. I don't ever use micro Teslas. It's the first time I've actually seen that unit. Well, whatever.
So wait, did you say it was Bill equals MG?
Well, free body diagram. What are the forces acting on that wire? Get the obvious one. What else? It's not falling down, so there has to be a force up. They used FM, magnet. I don't like M for magnet, because to me, anytime I see M, I think mass. And I want to get used to reinforcing to you folks that B is magnetic field, so I call it FB. And FB is, and yeah, that's where you'll go with that one. And this does give you a way to use magnets to a magnetic field to lift something or suspend something or hold something in place. And now, Sydney, we're starting to get into the very basics of, hey, now I can use circuits to move stuff or suspend stuff or apply a force. Question?
So B is the magnetic field, and that's what
B is what?
the magnetic field.
B is the symbol for magnetic field. And since it says find the force and direction, or the magnitude and direction of the magnetic field, and B is the magnetic field, I think that's what we're trying to find. Yep. Any others? By the way, a follow-up question to this, and I'm just making this up. I don't even know if I have this anywhere. Part A, find the magnitude of the force. Part B, I could tell you the length of the solenoid and the current of the solenoid. How many turns of wire would I need to make that magnetic field? Because remember, as soon as you know B, you can also then go to the solenoid equation and find N or I or L. There's 4 variables in there, and you 3 find the fourth. Next, any others? 3? Okay, did you try it? Okay. A beam of alpha particles. Now, you guys, most of you have done some chemistry. Alpha is positively charged, which is good because you were away. We did the right-hand rule. If it's an electron moving, our rule doesn't work. An electron moving up is the same as a proton moving down. If an electron moving to the left is the same as a proton moving to the right, we point our thumb in the opposite direction of electrons, of negative charges. But alpha particles are positively charged. Which way do magnetic fields go, from what to what?
Positive.
No, there's no positive magnetic fields. We don't call them. Which way do magnetic fields go? No such thing as a positive magnetic field. It's not what we call it. Okay, we call it north and south poles. Which way do magnetic fields go? So, Gabby, in this diagram, the magnetic field is this way. Okay?
Okay.
Then I would say charge moving that way, magnetic field this way. Which way is my palm pointing, Gabby? Up the page. You know what? It's going to get deflected upwards.
Okay.
That's the direction up the page. And then B, it says if the magnetic field strength, blah, 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 blah. Well, magnetic force on a charge is Q, V, B. Oh, they've given me the speed. They've given me the magnetic field, 6.4 Tesla. Ooh, that's huge. What's the charge? It's 2 protons. 2 times 1.6 times 10 to negative 19. If I gave you this on a test, I would clearly tell you, because that's a little chemistry we snuck in there. I would tell you that the charge was 2 protons, but in the homework, I don't mind. That's actually, I think you guys do that a little bit in Science 10, actually, right? Ions and stuff. Oh, never mind. What did I write right there? An alpha particle has a charge of 2 protons. So 2 times 1.6 times 10 to negative 19.
Okay. I
Yep.
was just confused with the stuff.
Yep. Those are magnets, right? Any others? Okay, so if you haven't done these, sunny weekend, and I recognize the sunny weekend, don't get graduitis. You want to really make sure you get through them by Wednesday for sure. Did you try number 5?
I did, but I don't know.
Okay.
Using our formula.
I don't know. What are they asking me to find?
Magnetic field strength.
And we're talking about a solenoid. So the magnetic field strength, remember, magnetic field, not a force, magnetic field Teslas. Magnetic field of a solenoid is mu naught Ni over L. You made that 0.15?
Yeah, I did.
You did that?
No, I put 0.01.
Oh, 15 centimeters is 0.15.
Sorry. There you go. I figured it out.
You are so good to be her friend, Jake. I'm understanding those test scores a little more now. Figure if I really make you mad, you won't do it on the test, which is, by the way, you guys have clued in. Anytime you make a dumb mistake, I put my finger out and press because I'm hoping that'll make you so ticked off you'll be furious on the test and won't do it, right? Anger is a good emotion on the test, I think. Any others? I'm sensing some of you haven't done. Again, I'll take questions on this next class. Or maybe I really nailed the lesson and you all did it really well. That's fine. Let us move on then to lesson 3. The final lesson of this unit, this short unit. So today we're looking at applications of magnetic forces. A few of the things that you can do with this. And you can do some pretty cool stuff. The first application that I wanted to look at is the current balance. You can use, if you take a rectangular strip of wire, you can apply a force on it using the solenoid, and if you put a mass on the other end, you can balance it like a teeter-totter and make a current balance. And it is a cool application, and I would normally spend more time on it, but we're a bit behind, so I'm actually going to say I'm not going to look at the current balance, although it's nerdly cool. I'm not going to look at the current balance. I'm not going to look at the current balance. What I am going to look at and assess you on is the cathode ray tube revisited. The television up until a few years ago when the flat screens came out. How television used to work. You may recall we said that you could, with an electron gun, use parallel plates to deflect an electron beam up or down or left or right, and that would then hit a phosphorescent screen and a little dot would appear, and if you did that really fast so that your eyes couldn't spot it, the speed, you saw an image on the other side. That's how a TV screen worked. In reality, we don't use parallel plates because parallel plates have to be long. We don't use parallel plates to deflect the electron beam. Instead, we use solenoids. We use solenoids because you can build them vertically, very compact. So, I wrote here, in actuality, we don't use parallel plates to deflect electrons in a cathode ray tube. Instead, we use solenoids. So here's a diagram. And then I wrote, solenoid M can deflect an electron. So let's review here. Here is our electron gun coming towards us out of the page. Now, electrons coming towards us out of the page, we don't use our right-hand rule for electrons. We use our right-hand rule for protons. So electrons coming towards us out of the page is going to be the same as protons going which way? Into the page. So when we do our right-hand rule, we'll point it that way. Now, this solenoid here, solenoid M, this vertical solenoid, it can create a magnetic field. it can create a magnetic field right here. And what I'd like to figure out is what direction. So we're going to use our right-hand solenoid rule. What was our right-hand solenoid rule? For the right-hand solenoid rule, what you did is you imagined holding the solenoid in your hand. And depending on which way you curled your fingers, the current, your thumb pointed north. So if you all want to give me a thumbs up right now, imagine you're holding this one in your hand. You can either have a north pole on the top, yes, or you could have a north pole on the bottom, depending on which way I run the current. What I want you to realize is right here, from solenoid M, either the magnetic field is pointing down or up. Down or up. I don't care which way right now. All I know is solenoid M gives me a vertical magnetic field. And just for the sake of argument, just for our particular example, let us temporarily pretend it is pointing down. I don't want to write it on my diagram because my diagram is going to get really, really yucky. I'm going to label it right now and then erase it. Don't you write it on your diagram because we really mark this thing up. But for now, let's pretend that the magnetic field here, for now, is pointing, come on, pen, that way. Don't write that down. Don't write that down, as I said like 5 times now. Okay, I'm going to really mark this diagram up. So let's put it all together. Electrons coming out of the page is the same as protons going which way? So point your thumbs into your page, or you can use my whiteboard, my board up here. And we have a magnetic field pointing which way? Magnetic field pointing which way? So point your thumbs down. You got to bend it a little bit. If that was the case, which way would these electrons get deflected? I think to our left. Yes? And what if instead of having the magnetic field pointing down, what if I reverse the current? Which way would the magnetic field be pointing? It's meant to be really obvious. If I reverse the current on a solenoid, which way will the magnetic field be pointing if it was really pointing down? Up. Okay. So up would be like that, still into the page with my thumb. That would deflect it to the right. You know what? A vertical solenoid gives you a horizontal left-right deflection. Because of that right-hand rule, everything's perpendicular. What I want you to notice is that solenoid M can deflect the electron left or right. Hey, if a vertical solenoid can give you a horizontal deflection, what do you think solenoid N, a horizontal solenoid, can give you? Let's convince ourselves. So let's hold solenoid N in our hand. It looks like I can either have a magnetic field going that way or that way. Right there, I can either have a magnetic field pointing to the left or to the right. So electron coming out of the page, proton going into the page. If I have the magnetic field pointing to the left, like that, which way is my palm pointing? Up. It would deflect it up. If I have the magnetic field pointing to the right, point it down. It turns out solenoid N can deflect the electron up or down. And Jaron, this really gives us exquisite control, because remember I also said the force on the electron, the force of deflection is QVB. I don't change Q, it's an electron. I don't change V, velocity, but what I change is B. But what's creating the magnetic field? Solenoids. And we just said last lesson, remember that the magnetic field of a solenoid was mu naught Ni over L. I can really control that with a lot of accuracy. Easiest way, to be honest, because I don't want to change the other parameters, I just change the current. That is what, I'm assuming you all grew up with a regular TV, an old style TV. That is what the Cablevision box, the Cablevision, that's what it was sending to the TV, was current fluctuations. That's all it was sending. Everything else was taking care of itself. Oh, and this is a black and white TV. Jason, you may recall we said for color TV, there was 3 electron guns and 3 different phosphorescent chemicals. You got the red, cyan, and effect. Okay. Just to show you, so let's look at some examples here. Example 1. We're going to try this. I don't want you to blurt the answer because these are tricky right-hand rule questions, so you can try and think about the answer on yourself. An undeflected electron beam strikes the center of a cathode ray tube. A solenoid placed inside or beside a cathode ray tube causes the electron beam to strike the screen at position X. So initially, when we flip the solenoid on, it's hitting at location X. It's getting deflected down and a little. What changes to the magnitude and the direction of the current in the solenoid would cause the electron beam to strike the screen at location Y? What changes would you make to the solenoid if you wanted the deflection to be up and bigger? Think about it without blurting out an answer. See if you can circle what you think is the correct answer. And if someone thinks they're right, you can try and convince me that you're right. I think that the first part, the magnitude of the current, I think that's easier. Do you think a bigger deflection would need a bigger current or a smaller current? Bigger. Can you bigger force? And force is QVB, which B mu naught Ni over L. So you know what? Let's write some of this down. The force of deflection on the charge is QVB, and this from a solenoid is mu naught Ni over L. So if I want to bump the force up, yeah, I think I can bump the current up. Increase it, increase it. How would I change it from being deflected downwards to being deflected upwards? Reverse it. In fact, you know what? I can even tell you what direction the current must be going in that solenoid to get to location Y. Which way did Y get deflected, up or down? Up. So all of you take your right hands, hold your palms pointing up. Okay? Now, the electrons are coming out of the page towards us. Yes? That's the same as protons going which way? So if I go like this, and I want my palm pointing up, I got to bend like this. The only way I can do that is if I have a magnetic field pointing to your, which direction is that for you guys? To your left. So the only way that works is if the magnetic field is pointing to the left right there. In other words, this has to be north and this has to be south. Now I can hold the solenoid in my hand to get that to be a north pole. You know what? The current has to be going over the top and away from me. The current has to be going over the top and away. I didn't ask that, but for what it's worth, I could have. The reason I didn't ask that is I couldn't get this diagram very clear. It's kind of smudgy. It's probably worse on your copy, yeah? Oh, here's a smudgy diagram that we're going to have to figure out. I'm going to have to zoom in like crazy to see if I can get this. It says, when the electromagnet is turned off, the electrons in a cathode ray tube strike the center of the screen as shown. When you turn it on, where will the electron beam now strike the screen? There's the solenoid in the picture. See it? Is that solenoid vertical or horizontal? Vertical. Which way will my deflection be? Vertical or horizontal? So you know what? I can already say 1 and 3, no. I know it's going to be some kind of a horizontal. It's going to be to the left or to the right. Which way? Now you have to follow it here, and I'm going to zoom in as much as I can, but it looks like the positives, if you the current, if you really zoom in, I think it's, if we are holding the solenoid, I think it's going around towards us and underneath away from us. So with your right hand, hold the solenoid like this, and which way is my thumb pointing? North. So in this solenoid set up, hooked up this way, that's north, that's south. The magnetic field would look like this. And if I follow it right where the electron is, what direction is my arrow pointing? Up or down? If I follow it right where the electron is, what direction is my arrow pointing? Up or down? Up, because magnetic field lines point from what to what? Now here I don't have a north pole down here, but I do have a to south. So magnetic field line would be pointing up. So magnetic field is up. Electron coming out of the page towards us, same as a proton going which way? So point your fingers into the page. Magnetic field is up. 2 or 4, which way will this electron be deflected? I gotta try this myself. Into the page. Is it not 4? Is your palm not pointing to the right? Dorothy? Right? Yeah? Direction 4? Direction 4? Direction 4?
Doesn't make any sense.
I won't give you this as a written, but you can expect on your test some kind of a multiple choice cathode ray tube kind of a question. So there's one application. The coolest application is the electric motor. Turn the page or next page, yeah, if you haven't already. Here's how electric motors work. Figure 7.28, blah, blah, blah. I'm just going to start. I want you to look at this picture here. Okay? This is a very, very simplified electric motor. In an electric motor, you have a magnet, a permanent magnet of some type, or it can be an electromagnet, but let's pretend it's a permanent magnet. So here is our permanent magnet. And in an electric motor, you have a coil of wires called the armature. To simplify it, Terry, I've just made it a single wire, but normally it's a bunch of wires, because the more wires, the stronger the motor. Okay? And what we do is we run a current through it. Now, right here, we're running a current up the page. Which way is the magnetic field? From what to what? So all of you point your right thumbs up the page. Magnetic field to the right. Which way will the left side of this coil feel a force? Well, we called the current into the page, right? So, will it not, down the page? Yes? Yes? Current into the page, magnetic field that way. It's going to feel a force. You got to kind of imagine tilting the diagram like this, right? It's going to feel a force down. Or, you know what? Here, look down the end of it right here. Current going away from me, it's going to feel a force down. But look, on the other side, which way is the current moving? Once it goes around this loop, which way is it moving? Towards me? Magnetic field that way. Which way will it feel a force? Use this diagram if you need to. Towards me, magnetic field. Which way will it feel a force? What did you say, Megan? Not only that, look, it'll spin. Look, it'll spin. Won't it? If the left side gets forced downwards and the right side gets forced upwards, it's going to spin. Now, if that's all we had, we'd have a problem, because as soon as it flipped over, now I'd have this current on this side, this current on that side, and it would come to a stop. So what we need is some way, once it starts spinning, to let its momentum keep going. We need to have some way so that the current is always flowing up on the left-hand side, or away from us on the left-hand side, and always flowing down or right on the right-hand side. Now, the easy way is alternating current. That's one way. But most electric motors run off direct current. So here's what we do. We put a piece of metal shaped like a hamburger, but with no patty. So 2 hamburger buns with a space between them. And rather than having this all connected with permanent wires, we have metal brushes right there and right there, so that those metal brushes can conduct a current still, but the center portion is free to rotate. When you do that, what happens? It's much easier if I show you an animated video. Now let's read through this then. Lots of information and terminology. Oh, I need to go to that animation, don't I? The electric motor. Figure 7.28 shows a simple one-turn coil motor operated on direct current. The coil in a motor is called the armature. You will need to know that word in that I will use that word in questions. Of course, a real motor will have many turns of wire. In my diagram, I just gave you one. The external or field magnet may be an electromagnet rather than a permanent magnet. So this outside magnet right here, it can be permanent or it can be a solenoid, electromagnet. Usually it's an electromagnet. The external magnetic field exerts a torque on the armature. It exerts an upwards and a downwards force on opposite sides. Torque is going to spin, causing it to turn continuously. Note the importance of the split ring commutator. Also a word you need to be familiar with. When the armature makes a half turn, the split ring commutator causes the current in the two halves to change direction so that the magnetic force and therefore the torque is always down on the left and up on the right. Or if you flip the current, down on the right and up on the left. But you can spin it whichever way you want to. So this shows the construction of a typical laboratory. Do I have it here? Oh yeah. Here's the construction of a typical laboratory demo motor called a St. Louis motor, and it walks you through it. I wrote for a nice animation. Do I still have that animation? Let me just see. Gotta pause the video again. So nice application, the electric motor. Is there more on the page for you guys or not? Is there a turn the page? There is? Okay, why can't I turn the page? What's going on here? Okay, a little strange. Electric motors come in all sizes. Some are very tiny and drive toys. Others are huge and drive trains or buses. You'll find electric motors in toy trains, automobiles, clocks, wheelchairs, streetcars, can opener, well, lots and lots of places. The motors described that I've just shown you operate only on direct current. Alternating current work on essentially the same principle, but Jason, you don't need that gap half hamburger shaped split ring commutator in the middle there to flip the current for you. It'll automatically flip the current. The only issue then is your speed almost always becomes a function of how fast the current alternates. So the other reason you go with direct current is it's easier to modulate the speed just by changing the magnitude of the current. With alternating current, the speed is going to be a function of the frequency of the current change. That is much more difficult to change because that comes from the generator that created it. Okay. What's your homework? We are done the unit. Your homework is... Come on.